So my name's Jay. I'm going to be talking about Apache Kafka. I'm going to be talking about what it was built for, how it's put to use. I'm going to be talking about event streams. This is going to be one of those talks that combines about 5 years of work into an hour. So I'll accomplish that by talking fast. Previously, I was at LinkedIn, and I'm now at a small startup called Confluent, which I'll mention briefly. And at LinkedIn, I worked on Kafka. I was one of the people who helped build it with a couple of my co-founders at Confluent. I worked on other data infrastructure systems there, the Hadoop rollout. I built a key value store called Voldemort. I worked on a bunch of random stuff, and previously worked on a bunch of the kind of like data-centric problems. So that's my background. All right, there's going to be a couple of themes in the talk. I'm going to try this where I give the themes up front, and then, I don't know, you can spot them. This is like the Cliff Notes. So if you just make it through the next 3 slides, you can like duck out and be like, oh, yeah, I saw that talk. It was about like A, B, and C, right? So the first theme, and I don't know, I picked up on this in a bunch of the talks I saw here, is really the kind of rise of events and event data. This is, it shows up in all kinds of different ways, and I think it's showing up a lot more in computer programs now. I don't know, how many people were in the event sourcing talk next door just a second ago? Yeah, I thought that would have pretty good overlap. So I'm not really going to be talking about event sourcing, but this is a very similar idea, maybe at a slightly different scale, and I'll talk about that. But event data is showing up everywhere. So when people talk about log processing or log data in big data, what they really mean is event data that they happen to put usually in a log file. There's nothing essential about it that's a log file. It's event data. I think even traditional data warehousing is very event-centric. If you think about like a fact table in a data warehouse, that's a bunch of events. It's things that happened. And I actually think that this distinction is very deep, right? So traditional data infrastructure always represents state. And I think some of the more modern systems, some of this event sourcing thing, some of these other systems I'm going to describe, and Kafka itself is much more about events. And if you think about what computation is, anybody who was subjected to a computer science education, you probably had to see these things. Who knows what that is? Yeah, it's some kind of state machine, right? So you have states. You get inputs happen to you, and you kind of go between states. And this is one model of computation. And I didn't take much away from it when I was in school. I think I just learned it as like regular expressions or something like that. But actually, it's a pretty strong model of computation. It's very common in distributed systems. And there's 2 things here. There's states, the circles, and there's like events, the arrows, right? And so infrastructure has really mostly focused on the state, the tables, your product table, your customer table, whatever other table. And I think we're seeing a lot more focus now on the events, the transitions, and recording that. And so I think that's actually pretty interesting. Theme 2 here is immutability. And so there's this really interesting paper or talk, I think even a blog post on Immutability Everywhere. This was something Pat Helland, who's kind of a database guy, was talking about. I'm only going to be talking about one level here, but it's actually, immutability is kind of suddenly showing up at every level of the stack. So the functional programming people are talking about getting rid of mutable variables. And actually in 2 different ways, right? They're talking about like, well, let's get rid of like your counter and your for loop, which actually, never helped me that much. I mean, I don't have a big problem with for loops, but they're also talking about mutable process-wide state. And then in the data infrastructure space, this has come up in log-structured storage mechanisms. If you look at how HBase or Cassandra lay out data, it's very much a continuous sequence of changes or events or new row values. And then in distributed systems for the propagation of data, you have this kind of immutable stream of events. And the event sourcing people, of course, are all about this. And what I'm going to be talking about is actually a similar concept of immutable event fact data, but I'm going to be talking about it at a slightly different level of abstraction, which is theme 3, which is actually kind of in the large, right? So I think one of the interesting things that's happening now is people are taking as a level of abstraction everything happening within a company. And so you can see this in a bunch of different places. The traditional place you would see it is in the data warehouse, where you represent everything that happens in the company. The Mesos people, if you follow Mesos, I think there was a Mesos talk earlier, I think they've done a really good job of explaining themselves in these terms and talking about scheduling and managing processes at the data center level. And what I think a lot of the promise of these big distributed systems is being able to solve problems at that higher level. And I think when you do, actually a whole bunch of like new aspects of the problem and new things become available. All right, those are my 3 themes. Now I'm going to go through the talk. The rest of the talk is going to be much more experiential. This is kind of like, this is what happened to us, this is what we did, this is what we built, and this is what you can use it for. And I'll try and highlight some of those themes as I go through them. So I'm going to start with the problems we were facing when we started building this system. I was at LinkedIn. Like I said, I was kind of in the infrastructure space. I was originally working more on like data science-y problems, but over time came to be working more on like data plumbing problems, which is pretty much where I found myself to date. What I was, the story kind of starts in 2009, and the problem we were working on in 2009 was Hadoop adoption. And the idea here was to try and get a copy of everything we had in Hadoop. And Hadoop is a system, and in infrastructure or systems talks, you'll hear people really talk a lot about systems and what capabilities does it have. But when you think about like the use in your company, the value actually doesn't really come from the system. It comes from the system plus the data. And that was what we found when we did this adoption. So our task or our goal was to try and get a full copy of our LinkedIn, the entire organization, everything that was happening in Hadoop, so we could couple it with like kind of parallel large-scale processing. And we thought that would probably be a very valuable thing. And we didn't actually think it would be that hard, and it turned out to be very hard. It turned out to be hard for a lot of reasons. The first reason was our data was a mess. So it was like, events that were logged in some XML format and these CSV files we dumped out of databases, and we were spending a lot of time trying to like copy all these into Hadoop and translate them into structured Hive tables. And it was just kind of like a lot of manual work for each one of these. And our initial approach to this was just to kind of gut it out. Like basically, I don't know if you've ever heard this expression, but just kind of get it done. Just like put enough people on it, we'll get it done, it'll all work. And so we did a bunch of manual work to kind of clean up this data and make it visible. And we were like, okay, like we're done, right? And so we did some assessment of like what percentage of data had we actually captured. Like if 100% is everything happening in the company, what did we have? Our estimate was about 14%. And this is like a lot of work, right? So at that point, I mean, that was a little discouraging. But the result was kind of eye-opening, because even with 14%, we had a lot of problems. And so the problems we had, I talked about this data coverage problem. The other problem was just integration between all these different systems. Like we had relational databases, we had key value stores, we had log files, we had like metrics and operational data about what was happening in our data center. We had kind of ad hoc messaging systems. Each of these had kind of custom data formats, and each of them, the data was evolving all the time, right? You hire engineers to write computer programs, and as they do that, it generates new kinds of data and changes old kinds of data, and so your data is kind of constantly in flux. And so every time we were building these data collection pipelines, they were kind of becoming out of date as the data would evolve, and our mappings would all get messed up. And so that was how I got pulled into this area of thinking about data flow. Like how does it flow between stuff? And what we really wanted to do was get something that would handle this problem that would be kind of organizationally scalable, right? So I mean, it needed to be scalable in like the traditional sense of handling lots of data, but it had to be organizationally scalable in that we didn't want to have like a team of people whose job was just to translate things from A to B for each of these systems we adopted. And the result of that was I kind of ended up doing this kind of survey of every weird thing we were doing in the data flow area at LinkedIn, and it was interesting. So we had one way that we would handle kind of relational database changes. Of course, we had a bunch of different relational databases, but these would flow into caches. There was one mechanism for that that was pretty like low latency. They would flow into kind of replica databases. It would flow into the data warehouse. We would do CSV dumps. Each of these kind of had like a different time scale and different problems to scale it. We had NoSQL databases. Like we had this key value store that I'd helped to build. And we had like weird data flow from that to kind of populate it, because often it wasn't the primary store. We would have weird data flow back to kind of feed it data from Hadoop. I talked a little bit about those like user events. This is kind of like who clicked on what, or what did people search for, or what ads did we serve. There was a pipeline for those. It was kind of very ad hoc and batch collection. Whenever there's a step that's like rsync, things are not looking good. We had application logs, things like error logs and stuff that just went to Splunk. With messaging systems, kind of here and there throughout the organization, like no real central approach to messaging. We just had some like ActiveMQ instances that would be stood up as parts of individual applications. And then we had this kind of central monitoring system. And each of these kind of had pros and cons. Like some of them were high throughput and lossy. Some of them were low throughput and durable. Some of them were batch. Some of them were real time. But when you put them all together, it was basically like a giant mess. This is like our data flow architecture. And so if you're somebody who wants to get all the data into like a search system or into Hadoop or into like really anything, you're kind of like understanding this weird amalgam of different pipelines and all the properties of each of these pipelines and how they represent data. And so this was bad just because it was hard to keep it working. It was worse as our data grew and we had to scale each of these kind of pipelines. And it actually just made a lot of things difficult to do. So like, we were doing this Hadoop data acquisition effort, and one of the most basic things we'd like to do is analyze what was happening in our data center. Well, it turned out these operational data streams, they just went to a monitoring system. They didn't go anywhere else. And so like getting that data was like some huge project. And so you couldn't run like a SQL query in Hive to figure out what was the biggest bottleneck in your service call stack or whatever, which is like a totally reasonable thing to want to do. You could only analyze that stuff in real time. And then the flip side was we had this event data that went to like Hadoop and the data warehouse, but you couldn't do any monitoring on those kind of streams and get like low latency reporting on that. And so this is unfortunate. And being an infrastructure person, I was kind of interested in some kind of infrastructure solution to this problem. And so we kind of thought like, well, what do all of these different pipelines have in common? Or what should they have in common if they were done right? And we come up with this idea of having some kind of platform for stream data. The idea was like, well, you could kind of represent each of these flows of data as a stream of events. The event is just what happened. It's like an immutable fact. And it would represent different things in different ways. Like it could be an error that happened in an application. It could be a kind of business event, like, hey, somebody clicked on this, or we showed somebody this ad, or somebody did a search. It could be operational things like, hey, we restarted this service. It could be like a service call trace, like, hey, this service called this service, it took this long. It could be a change to a relational database. So like, we were very interested in that same kind of event sourcing use case, but we weren't really interested in rewriting our applications internally. We just wanted to capture the series of changes that were happening so we could feed those into search and we could feed those into other things. So maybe we were interested in half of the event sourcing story, maybe at a higher level. And so we had this idea of like, OK, we could have some kind of platform for stream data. It would be analogous to how we were using Hadoop in kind of the offline space, like some central platform. We could scale it out, collect everything in one place, represent these different things all the same. So regardless of which of these data sources you were interested in, it would just look like a stream of events. They would all be formatted the same. We could use that, hopefully, this is the hope, to load into Hadoop and replace all our ad hoc integration. And I could get rid of my team of data copying people. And so we set about trying to build this. And our first step was just to look at existing messaging systems. So the people who were working on this was me and two other people with like kind of a database background. So I'd previously built a key value store. The two other people on it, one had been like a database researcher and built like a Paxos-based data store, and the other had worked on Oracle. And so we didn't know anything about messaging systems at all. And so we thought, well, we should get some messaging systems and learn this area and try and build something on top of them that will be this in our company. So we started learning about like enterprise service buses and messaging systems. And we tried to roll them out against these use cases. And we ran into actually a bunch of issues. This is my representation of the success of our generation 1 project in this area. So the first issue was just throughput. Like for operational data or log data, that stuff is big. And so if you want to capture it all and you want that to be cost effective, it's really important that the cost of handling all that data is pretty low. And our estimate was, we were using ActiveMQ at that time. Our estimate was we would need as many ActiveMQ servers as we had other servers to do that. And that was like not, I mean, it's just the ratio, no matter what scale you're at, that ratio does not make sense. That data is not that valuable on a row per row basis that it justifies that. The second issue was around persistence of data for a long period of time. And that had to do with integration with batch systems. So we wanted to use this as the feed for Hadoop, the feed for the data warehouse, the feed for these systems that either load data periodically, like once an hour, or they may go down for maintenance for like hours while you upgrade, if you've done like a Hadoop upgrade. It's gotten a little better recently, but it's pretty painful. And so during that time period, of course, you have to store everything that is happening in a large consumer scale website, and you got to do that well. It can't be that you get slower as you get more data, right? The final issue we found was that the ordering guarantees in a lot of these systems, in the case where you have like parallel consumption, was not very strong. And that's really important for this case where you're tracking like database updates or mutations of data. Like if you have 2 profile update events in LinkedIn's case, and those are feeding into something which eventually goes into, say, a search index, it's really important that the search index gets the first update and then the second update. If it gets the second update and then the first update, it will be not eventually consistent, but inconsistent for all time, right, until that happens again. And so ordering is really important. And then partitioning, be able to scale this out. So these kind of deficiencies are what led us to try and take our own attempt at this problem. And this is the kind of reinvent the wheel approach. And so we thought, well, OK, we will build a messaging system of our own. And that's Kafka. And that's what I've been working on for a number of years now. And it is a messaging system. You have producers who send or publish events. They're stored in this cluster. They can be stored there and delivered in milliseconds, or they can be stored and delivered days later. Kind of it doesn't matter. And then you have these consumers who are the people who are getting the events. Each of these events is going to be published to a topic, which is like a category or feed of data. So in LinkedIn's case, there might be a topic which is page views. And there might be a topic which is like profile updates. And there might be a topic which is application restarts, and a topic which is like RPC calls inside the data center. Like pretty much each of these kind of high-level categories of activity is one topic. Those topics are, of course, spread out over this cluster. And then there would be consumers. So each of these topics is multi-subscriber. Multi meaning maybe 0 if nobody is interested in that stuff, but maybe many if it's a really popular data source. It's maybe going to go to search indexes and go to the Hadoop cluster and go to real-time processors that will react to it and process it in real time. So at a high level, we're just building like another messaging system. But our idea of what a messaging system would be was really, really different. So in terms of implementation, it's actually very different. So Kafka is built on this idea of a commit log, or a log of changes. And so this is my attempt at representing a log. And when I say log here, I don't necessarily mean like a text log, like an Apache log. I mean like a commit log in a database. So it's going to be a sequence of records, one after the other. Each of these numbered rectangles is meant to be a record. So the first record written is record 0. And then 1, 2, 3, 4, 5, 6, 7, you always append to the end of this log. And that's pretty much all there is to it. Readers who want to read that data will read from the left to the right. So when you read the log, you could read it in any order you want, I guess. But typically, you would want to read from the left to the right and get newer and newer events. And you can think of this record number as being a sort of time in some sense. It's a kind of discrete time. This is a really weird idea that's very common in distributed systems, but having some kind of logical notion of time. And so if you have read up to record 5, in some sense, you're at time 5. Who knows what like physical time that was if you checked your watch. But everyone who was reading could agree that time 5 was when you'd read everything before 5 and nothing after. And so it turns out that this type of commit log is actually a really good way to build publish-subscribe messaging. And this is not an idea that was unique to us. This is internally kind of the classical model of how a distributed system works. Like classical distributed systems is like state machine replication, where you have this log and those changes replicate out to the other replica machines, and that's how you keep everybody agreeing on the state of things. And so the only thing we did that was different is this is typically used inside a distributed system, so you would see it in like HBase or Spanner or MongoDB, God bless it, or whatever. And you wouldn't see it as a kind of thing in its own right. But I guess our thought was like, hey, if you look at what we're trying to do, if you look at all these different systems that are trying to sync off data, it's very much like a distributed system, right? We're trying to sync these different systems off of changes. It's just a really big distributed system. Like if you take all our stuff in the data center as one big distributed system, we'll use a similar technique. And so the way publish, subscribe messaging works with a log is you kind of, again, append to the end of the log. And then you have these readers who are at some point in time. And if you're at point in time 7, that means you've read everything prior to 7 and nothing after 7. And so if you have multiple systems, like maybe this is my Hadoop cluster, and maybe that's some search index. So the search index is like pretty caught up, but the Hadoop cluster is a little slower. I can reason about exactly what state those things are in. And I know that they all go through the same series of states, kind of in the same order. And so it's a very nice model in that respect. I can say, hey, what time is my Hadoop cluster up to? Well, it's up to time 7. So it has, I don't know, 4 more to go. And that is pretty much what Kafka does. So a topic in Kafka, which is this category of data, is going to be just a set of logs. So a topic is broken into partitions, and that's how we can spread load over a cluster. And each of those partitions is just a replicated, fault-tolerant log. And that's it. That's like really all there is to know about Kafka. So you can, if you want, you can leave now. That's like all it does. And so people are usually expecting something more exciting than that. But that's it. It just basically is a log abstraction. It just turns out that that's a really useful abstraction. I'll talk a little bit about what it's useful for. But before I do that, I'll mention a few things about the internals of how it works. So yeah, internally, in this diagram, these are servers. And A is a topic, and B is a topic. And 0 and 1 are partitions within that topic. And so I'm just going to show the data flow of how replication works. So there's a leader for each partition, and there's followers. If you write to the leader, it kind of replicates out to the followers. And we'll give very strong guarantees about when a row is written. So if you say, OK, I published this message, it will say, OK, I replicated out to my followers. I acknowledge your message. And the guarantee in that strongest mode of replication is if you kill one of these servers, it's not allowed to lose your write. And furthermore, that anybody who subscribes to these feeds, they will only see the same series of committed messages in the same order, even if somebody takes a write and then dies right away, or any of the kind of bad things that can happen in a distributed system. OK, and then this also comes with a way of scaling the consumers of data. So here are my partitions again. Those partitions are spread over servers. And now I can have different logical consumers. Like here I have this A consumer and this B consumer. And internally, those consumers are made up of logical processes. Now, they could be like just processes on the same machine or even threads in the same process, or they could be spread across many machines. And they will divide up those partitions amongst themselves. And each of them will consume the partitions it's assigned, and it will consume them in order. So we kind of give that guaranteed order, as well as scaling it out over multiple processes. And of course, if any of these consumer instances fails, we'll reassign the partition so that somebody else gets them. And this gives us this nice property that each of these processes kind of has, for each of its partitions, that point in time it's consumed up to. So I'm not going to go into a ton of other implementation details. I mean, that's kind of what there is. You can kind of read through the documentation and learn more about it, but it's basically that very simple abstraction. The primary effort, I think, is to take a simple abstraction, make it be the right abstraction for a lot of problems, and then make it work in the way it needs to work. And so in this case, coming back to our themes, we were interested in having this operate really at kind of a data center scale. So we could have 10,000 processes all connect to the Kafka cluster and log out everything that they were doing all the time, continuously, and be able to do that in a way that was operable and worked and was cheap, and would replace all those kind of different ad hoc data pipelines I described earlier. And you can kind of go through those different data pipelines I described, and you can think about what guarantees would you have to make that work, what properties would you have to make that work. So the first property is just being able to scale well for the high volume data. So if you want to take log events, errors, user clicks, impressions of things, you have to operate at relatively high throughput. So you have to be able to do 100 megabytes per second per server, or something, some multiple of that, something close to the disk and network throughput on a machine. you need to be able to hold many terabytes per server as well. So you can really just kind of grow this in a cost-effective way. To handle kind of the important data, you have to provide the guarantees that are not weaker than the database that you're replicating changes from, meaning strict ordering, which I talked about, strong ordering on when something is written, and guaranteeing that something is written will in fact be delivered. And then finally, we wanted to do this in a way that was distributed by default. One of the big differences I see in systems today is between systems that were built really to be a single server thing, and then you try and glue on some maybe distributed version of that. Like MySQL has like several distributed versions, but none of them were really kind of starting with the default assumption that everyone will run in a partitioned, replicated way. And when you start with that assumption, you actually get a pretty different system from the ground up. And I think that systems that are built that way, that you actually operate them really differently, and you think about them differently. You really think about writing to the cluster. You don't think about like, oh, I'm writing to this particular node or that particular node. You are able to kind of restart the individual machines in the cluster and do maintenance on them without stressing too much about that. And so you get this kind of very different way that the service operates, as well as the potential to share it across a bunch of different users. And then, of course, you want each of these layers to be fault tolerant and horizontally scalable. And so, OK, we built that system, and we started to put it into practice really for this use case, to act as this kind of central repository in LinkedIn for streaming data. And we basically went through different data sources, and we kind of just moved them onto this platform one at a time. We did all the user events. We did all the operational data, like metrics, service call tracing, errors. And we started on primary database changes, like somebody updated their profile. And this became the source for all kinds of interesting applications that fed off of that. So all kinds of monitoring platforms and analytical platforms, which I'm not going to go into great depth about. But it also opened up a whole other area, which was totally intentional on our part, which was stream processing, which was being able to take these feeds and process them in real time and derive results that were available in real time. And this was one of the things we designed for up front. This is something we were aware of. It was something that made a lot of sense, was that we would want to be able to do analytical processing off of these feeds of data. And so I'm going to take a quick digression and talk a little bit about stream processing. Usually when I dive into this area, people are a little skeptical of it. So stream processing, I think there's been a couple interesting talks that I think that touched on it here. But there's a lot of stuff in this infrastructure space, and so it's always hard to know what's kind of a fad or a niche and what's actually kind of a big deal. And I'm going to try and make an argument over the next couple of slides that this one is a big deal, that stream processing is a big thing, and that most people will end up doing a fair amount of it. Maybe not now, but soon. So the first thing I want to argue is, yeah, I mean, if you look at most companies today, there's not a ton of stream processing happening there. But there's also not a ton of stream data happening there. And it turns out that you can't do stream processing unless you have a real-time feed of data. You basically need Kafka before you get the processing layer, or whatever, like something like Kafka, right? And so most companies have batch data. And if you're getting daily CSV dumps, you're going to process daily CSV dumps. There's no way to process a daily CSV dump as a stream, because it is not. And this is, one illustration of this is if you ever talk to somebody who is a software engineer and not from the United States about the US Census, it's a very confusing thing. Like, you want to find out how many people are in the country. So every 10 years, you go around with a binder and a clipboard, and you ask, OK, are you in the country? Yes. OK, we got one, right? And you just do that for each person, and then every 10 years, you know how many people you had. Of course, by the time you're done asking, it's not right anymore. And of course, the way you would build something like this today is you would build our roads. Yeah, well, you would journal births and deaths, right? That's what you would do. You would journal births and deaths. And if you journaled births and deaths, you could compute not only how many people you currently had at this instant, but you would also have computed the number of people you had at every instant in the past, which would be like a much more obvious way of doing it. But obviously, at the time that we were coming up with censuses, the census, they didn't have like high-speed computer networks. They just had like horses. So they were definitely going to do a batch collection on horseback with sheets of paper. And this is actually not that different from the state in a lot of companies. Like, there isn't a lot of stream data, and so a lot of stuff kicks off, and you got the cron job or the data warehouse thing or the Hadoop job, that kicks off kind of every 24 hours and does some processing. All right, the second thing about stream processing that I'll say A lot of people think it's kind of a niche. I think it's actually a generalization of the processing models people are most familiar with. So it's a generalization, I think, of batch processing and request response processing. Let me say what I mean by that. So request response processing, this is kind of what people do a lot of. This is what most services are. This is like REST or RPC. I give you a request, you give me a response. I give you another request, you give me another response. It's great. There's nothing wrong with it. I think it's a good abstraction for many types of systems. The alternative of that is kind of batch processing. This is the opposite. Instead of giving you one input and you give me one output, I give you like all the inputs. And then like you think for a while, and then you give me all the outputs, right? And so these are two extremes. One input, one output, all inputs, all outputs. The obvious generalization is something which is in the middle, which is you have control over how many inputs you'll take before you give some outputs, and how many outputs you'll give, okay? That's what stream processing is. It's just basically being able to kind of move the slider between very delayed processing and kind of one input turns into one output. Thought about that way, this is actually pretty broad, right? What is the space of things that are in a company that are asynchronous, but it would be nice if they were quick? I think it's pretty broad. I think it's probably about 30%. It's not everything, but it's probably about 30%. And what does this have to do with Kafka or logs or any of that stuff? Well, like in my worldview, stream processing, that kind of like log abstraction is really the kind of physical representation of a stream. It's a set of changes that happen in some order, and processing of that stream is just a program. So anything which subscribes to that stream and computes something and produces some output, it's doing stream processing, right? I mean, I don't know, maybe it doesn't sound that fancy, but it's doing stream processing. You can do this off any messaging system. There's nothing specific about Kafka, although this is a Kafka talk, so I've used that. And that may go to something else which does transformation and produces output. And everybody is familiar with this model because of Unix, right? If you have a program and it pipes to another program, that does computation off of it and pipes to another program. The only difference here is, of course, Kafka, the little pipe symbol is what Kafka would represent. Kafka is multi-subscriber, so you can pipe to multiple things. And it's also named, like you would publish to a named topic. They have that in Unix, but not as many people know about it. And of course, in this asynchronous model, your goal is always to produce output into some kind of live request-response data store. Right? You're computing a materialized view or derived view of your data. You're computing counts. You're computing something that would eventually be served to users. Users are usually real-time people. But you don't have to do this just with your own code. There's actually a number of frameworks that pair really well with Kafka that will help with this. Storm is one of them. Samza is one that we worked on at LinkedIn. Spark streaming is another one. If Kafka is some kind of like representation of a stream, these are basically processing layers that help you write that program that subscribes and processes. So it's kind of like stream plus processing equals stream processing. That's as much math as this talk has. And so coming back to that Unix pipe analogy, you can kind of think of this as being kind of an attempt at a modern version of Unix pipes. Unix pipes are not the greatest thing in the world, but they do actually allow a bunch of programs to share data without all those programs being custom integrated one to the other. And so maybe, that's actually a pretty good thing. If you think about like modern architectures, we're not even that good. So this is kind of like that. It's just done at that data center level. And I think it actually becomes very interesting when you kind of up-level it to the data center level. So there's actually, of course, a lot more you need to make that vision complete. I've talked about like infrastructure. There's actually a ton about data format, which I'm not going to go into. We spent a bunch of time like getting good representations of data and being able to, propagate the schema of our data all the way through to consumers so that, you didn't have to like manually file a ticket to change the schema in Hadoop if your event updated. That's like a super deep area I'm not going to talk about. I'll leave you with this one thought, which is like, a lot of people these days are very down on schemas, but maybe those are actually just deficiencies in systems that they used that handled schemas. So like if you're using a database and its view of the world is there's only one schema at a time, which some databases have that limitation, and yet your code changes, you have like many apps and they don't all update like all at once because you don't bring everything down. That's like a big mismatch. It's very hard to work with. And if changing schemas is very difficult and painful, like takes a day of whatever to update all your data, that's really painful. That's like basically bad schemas. And so people are like, forget schemas, that's terrible. But of course, data has structure, and you want to capture that and make use of it. So there's a whole other talk I could give, which is really around representing data well and flowing it in contracts to people and keeping your data clean and beautiful kind of at a company-wide scale. And it's something we're kind of doing some work on, but is a little bit outside of the scope of this, which is more of an infrastructure-centric talk. So anyhow, we did this. When you put it all together, this is kind of what you get. So we had, I don't know how visible these diagrams are, but I guess it is what it is. So we had all these different data feeds that would come into kind of a central Kafka message bus. And that would capture what was happening in databases. It would capture all this event data. We weren't doing event sourcing in the sense that we didn't rewrite our applications to store their internal stuff here. We just captured the events, if that makes sense. You get a lot of the benefits if you just do that, sort of a smaller commitment. There are actually some interesting projects at LinkedIn, including this newsfeed application and some of these other big distributed systems that actually moved towards a fully event-sourced model where they used that primary log as the stream that fed them. It was pretty cool. But even without that, I think you get a lot of the benefit. So anyhow, in this architecture, we basically had this kind of central feed of everything that was happening in the company available in real time. We had a stream processing layer that could subscribe to that and kind of publish back new derived feeds. So you could take streams of events. You could join on attributes of the user that had done that event. You could compute things off of that and publish it as a stream. All of the streams you published back could go back into these live serving systems to be kind of indexed and served. They could go to these kind of real-time systems that would feed off of it. They could go to Hadoop or the warehouse space for kind of long-term archival. And this ran at really big scale. We kind of did the experiment of representing everything as a real-time stream. That meant we had, I think as of recently, about 800 billion messages written per day and 2.9 trillion messages read. Since it's multi-subscriber, you would have more things read than written, you would hope. And that's about a petabyte of data that was stored, this kind of stream data. And in any of these data centers, there would be thousands of processes that would be connected. In fact, every process in the data center would connect to publish at least errors and statistics and operational stuff, even if it had no other data streams to produce. As I mentioned, it ended up being the kind of backbone for a number of these data stores. This would be how we would munge and feed data into search and the social graph systems, the kind of news feed that's on the home page. And they're actually doing a project now, which is pretty exciting, to convert the primary store for data to use Kafka as the kind of commit log, which is pretty cool. And this became the basis for all that kind of stream processing or asynchronous processing. And it's an open source project, so it's actually used at a variety of companies in similar ways, but in very different industries. It turns out events are not a web company thing. Events are pretty common. And anyhow, so after that experience of working on this for about 5 years, we really became convinced it was a big thing for a number of reasons, right? The system diversity is kind of increasing, so that integration layer that kind of glues everything together is important. Data diversity is increasing, so like the fact that we're now very interested in log data or what happened for analytics, that's kind of another pressure. I think the world is just getting faster. Like for any kind of consumer-focused application, people do not understand if you do something and then it's reflected back in the product like a day later. Like people don't understand batch programming. They don't understand if they update something here and it takes like a day to update over there. And then of course this technology exists now, so it's a lot easier to do. So we became convinced that this was like a really big deal and that these kind of event streams were going to be a kind of central part of companies. And so we quit our jobs and started a company to do it. And that's what I'm doing today. So we're really just trying to make this practical. We're working on Kafka and kind of finishing that infrastructure layer, really making it something that can run in a company that has sufficient security and multi-tenancy and everything to work in all the different companies, and just finishing that system. Dealing with a lot of the other problems that we dealt with internally, like metadata and schemas and monitoring data flow and connecting up to common systems and making stream processing actually something that's really easy to work with. And so that's what I'm up to now. If you're interested in this stuff, you probably can't read that, but if you could, there's a long blog post on a lot of the practicalities of what we did. So if you kind of Google for like stream data platform, you'd probably find that. And then there's a longish blog post that has a lot of the same material that's in this talk. And you can either get that as a blog post or you can get it as a book if you like books better than blogs. They're pretty much the same. And then I'm on Twitter. And that's it. I'd be happy to take questions from anyone who has them.
Thanks, Jay. 800 billion messages written per day. All right. How many clusters was that across, and how many total nodes?
Yeah, it ended up, so here was how we did it. The goal was always actually just to have one cluster per data center. But we didn't have as much in the way of multi-tenancy as I think we will by the time of the next release. So we separated it by large categories of data. So the way we would come up with clusters was, first of all, each data center was like its own world. And then we would mirror data between data centers to create the aggregate view. And then secondly, we separated operational data like error logs, metrics, that kind of stuff from primary data from really critical data. And so that was the big separation. So there would be a handful of clusters per data center.
OK. So sorry, one follow-up question. We're about to build Kafka as our backbone for event receipt. Mm-hmm. And one of the things that keeps me up at night is, well, what if the cluster goes down? Mm-hmm. So do I have to build a Kafka that protects from Kafka? Or, I mean, what's your experience with the cluster being down and the horror of not being able to accept events?
Yeah, I mean, I think that question is kind of like, well, does it work? And the answer is yes. But it's one of these, A, it's new, and B, it's a distributed system, both of which should make you cautious, right? So yeah, it works. We ran this thing at very large scale. We did auditing that was fairly exact. So we would track everything we thought we sent, everything we thought arrived, everything that would mirror between data centers, everything that we thought was received, and then we would compare across these. And so you had to prove that it worked, right? And so I think the answer is yes, it can be run reliably. Like any distributed system, you kind of have to know a little bit about how it works. Maybe you should come talk to this Confluent company. I don't know. But yeah, so yeah, it's in a working state now. It's not super buggy. Can be run reliably. Is run at a large number of companies and used for important stuff. But like any distributed system, I would run it for something unimportant to make sure you got that before you're putting the I don't know, the billing information in or whatever. Any other questions?
So, two questions. One is, what are you actually seeing in terms of real-world performance versus an ActiveMQ? And the second question is, how would you work with something that did require truly a queue, where you want one consumer to receive any given log event?
Yeah, let me try and answer both those questions. So the first is around performance. So we did pretty detailed benchmarks against ActiveMQ a couple years ago. Like all of these projects get better all the time, and so that's a little bit unfair. I've seen other benchmarks. I don't know that they were that good out there, so you can kind of get that. I did a very detailed Kafka benchmark. If you just go to the Kafka page and look at performance, it'll give you that. We've kind of avoided doing head-to-head comparisons. This is an area where we win by a lot, so it looks like either we're cheating or something. We're not cheating. We're just better at batching data and efficient I/O and basic system stuff. So yeah, the performance is basically pretty good. With reasonable message sizes, you should be able to saturate your kind of network throughput. And that's actually not necessarily true for messaging systems. It's particularly not true for messaging systems that are persisting data. So the comparison for Kafka and these other systems would actually be when you turn on all the dangerous options like replication and fault tolerance. And once you turn that stuff on, you're pretty hosed on a lot of those things. So yeah, I don't know if I would have a particular benchmark I would recommend. You can check out the Kafka benchmarks, and then you can compare it to some of the other system benchmarks that people have done. It's usually an apples to oranges comparison because it's not necessarily on the same hardware. But you can also try it yourself. I think it's This is an area where I think there's a pretty clear difference. Oh, yeah, queues. So you said, what if you want a true message queue where one message fans out to everybody? I would actually think of that more like a topic or pub sub than a queue. But yeah, you can totally get that. So that model I described, if you know like JMS terminology, in which case I apologize, but if you know JMS terminology, they have topics which kind of broadcast out, and they have queues where it goes to like one person. That model I described generalizes those two concepts. So between groups, we broadcast, and within a group, it's a queue. And so if everybody is their own group, then it's totally broadcast. If everybody is in the same group, it's totally a queue. But the nice thing about this is you can have like multiple groups, and you can get everything in between, which is, in practice, I think what you want, because you usually don't have, usually a consumer is not like one process. It's usually like a pool of processes, like, hey, we're sending these to the search cluster. Doesn't mean that every consumer gets every event. If your event stream is large, that will be like physically impossible. So the nice thing is you can turn that knob from everybody gets everything to we divide, and you can do that at whatever level you want. If for whatever reason, that consumer group concept is sort of like mind-blowing. I actually think it's much simpler than having two totally distinct abstractions like topics and queues, but it requires some adjustment. So there's some explanation on the website that kind of goes through some examples of that that may be helpful. Question?
So you didn't mention it, but it seems like you're a fan of Avro.
Oh, yeah. Avro. Yeah, so like I said, there could be a whole other talk on data formats and schemas and whatever. The most important thing is basically if you're rolling out something like this, I think picking a standard data format in the company is just like hugely valuable. And people, for whatever reason, don't do this. And it actually really sucks. Like if you have 20 different ways of representing data, the poor people who want to consume many of these are just like stuck doing it all. And if somebody had just like made a decision, like whatever your worst choice was probably better. I mean, well, okay, maybe not your worst choice, but your second worst choice. So there are a bunch of technical advantages for Avro for stored data. The way it does compatibility is much better. The problem with JSON is basically it's very verbose. So for large data, that actually ends up being a problem. Like half your data is basically field names. Other than that, JSON's fantastic. The JSON schema stuff is not as good. So if you want to have some kind of contract with people, it's a little hard. I'm usually suspicious of contracts, but in this area where I publish data and it like fans out to many people who I may not have met, some kind of contract is actually useful. Just being able to document, hey, here's the set of enumerated values that can appear here is valuable. And Avro does this a lot better than something like protocol buffers, where like the binary format is just like some tags, and everything else is in like generated code. That's obviously hard at an organizational scale where it's like, hey, can I come get your generated code? So I understand what your fields are. That's like not great. Yeah. So anyhow, there's lots of ways to do this, but like if you are highly opinionated, awesome. If you're not, I would probably just use Avro. We made some tools that help with that. Other questions? Okay. I can also just repeat the question if. Yeah, that's pretty common. I mean, I guess it depends what you mean by that. Yeah, the question is how many people use this as a durable database? So the reality is anything which is in between you and your data is a system of record for some period of time, right? And so the question is like, is it feasible to do that for a long period of time? The answer is yeah. Like the stream processing system we built uses that for state information, which is essentially persisted forever. People use this as a database change replication mechanism. And we have a feature which will actually compact that log so it keeps like a full set of data you can load off of. Those features are pretty well used. There's nothing bad about storing a lot of data. Your performance when you have 5 terabytes of data on disk will be the same as your performance when you have 1 megabyte of data on disk. It doesn't scale down with data. So yeah, it works pretty well. Like anything that stores data, you need to know how to manage it. Like I would always advocate people have a reasonable number of persistent systems just because they're a pain in the butt, and know how they work, right? So yeah, I think like if you are familiar with the system, I think it can absolutely be used as a persistent store. But obviously, if you're doing that, you would want some advantage over whatever the alternative system was.
Two questions, just going back to the sort of the beginning of the talk when you're talking about the log structure
Yeah.
of the messages, and that is in terms of both persistent versus transient consumers and just general consumption, interleaving streams. How does that work in terms of log cleanup?
Yeah. So I think your question is, we have this log of events. When do we get rid of stuff? Is that what you're asking? Yeah.
How do you defrag it?
Yeah. OK, so the way that works in most messaging systems is they try and get rid of messages right away. Like, as soon as it gets to somebody, you delete it. And the reason for that is because they don't handle persistence well. And so if they don't delete it quickly, they're going to get really slow. And that's actually bad, because if you ever have one slow consumer, it will back up data, and then it's really bad, right? So we take the opposite approach. The thought process is this. You have to plan for that worst case where you have a slow consumer. Imagine you're doing this at data center scale. Somebody's going to be slow. Somebody's always slow, right? So you have to plan around that case. So instead of trying to throw stuff away right away, just have an SLA and say, we will keep your data for 7 days, or we will keep your data for 3 days, or we will keep your data for an hour. So that is the way it works in Kafka. We basically retain that log data for a period of time, because you can store a ton of stuff that doesn't usually get pressing. If you can't get your thing back working in 7 days, it's probably not that. At that point, it's really broken. So it just works on an SLA. In practice, with any messaging system, you only have so much space. So you always have that SLA. It's not like you can necessarily buffer data forever, even if you're exact about it. We also have a feature for mutable data, like database changes, which does compaction. So in that case, instead of retaining updates for 7 days, you would retain the recent updates plus one update for each key, or whatever. That's kind of useful in that event sourcing or change, mutable data. That's a more advanced topic. The simple answer, I think, is by time, by size, or by number of messages. Cool.
What's the rule of thumb when it comes to how many partitions you need to have for a particular topic? And the second question is, I guess you do that when you create the topic, you specify how many partitions you want to have. Can you update that once you have more consumers consuming your data?
Yeah. So that's a good question. So the rule of thumb for how many partitions to have is based on the maximum number of consumers you would want to have. So we use an over-partitioning model. You can have 100 partitions and put them on one machine. Then you could add 10 machines and move them around. Then you could add 100 machines and move them all around so everybody had one partition. If you had 101 machines and only 100 total partitions, one machine would not have any work to do. So because we have this in-order consumption model, that number of partitions does determine the maximum number of consumers you can have at any given time. So that's how to make the choice. There's some trade-offs involved. So we wrote a pretty detailed blog. If you go to that blog.confluent.io, it'll give you all the trade-offs. But most people just pick some reasonable number and go with it. You can, in fact, up it later if you want to. However, if you're partitioning by some kind of primary key, when you add more partitions, we don't repartition your data. We just add the new ones. So anyhow, the good answer is Google Confluent Kafka partition block, and you will find a much longer answer. Any other questions?
I wouldn't mind actually going back to a question asked a moment ago about using this as sort of the system of record or the durable database. Because by my own interpretation, we've had at least 2 talks prior to this one, which basically said event sourcing and command query responsibility segregation is the way of the future. It's going to solve lots of problems.
Yeah.
And in theory, a bunch of people are going to walk away from this conference and install Kafka as their database.
Yep.
At least 50% of the people in this room are going to do that. So I guess
is that how it works? Whatever people say up here, it's just
so I guess at a high level, I'm curious about your thought about that statement, that it is not just a good tool for some jobs, but the way that it's going to be going forward.
Let me comment on that. So I think you're saying, is events, I think there's a couple questions here. One is kind of the Kafka, does it work question. The second, let me come back, I'll try and address that in more detail. The second is event sourcing, is this going to make my life 1,000 times better? That's a really interesting question. So first of all, I don't know, all right? One of the things I thought was not that well handled in the event sourcing world was how to deal with big partitioned data sets, which is like the world I came from. And so like we didn't build a ton of event-sourced applications in the traditional way. What we built were actually event-sourced partitioned data systems, because you always had to like have the data system just to deal with like partitioning and that kind of stuff. So I'm not sure that that problem is as well handled as people say. When I talk to event sourcing people, they're like, oh yeah, partitioning is just like MySQL, you just shard it. And I'm like, yeah, that's hard, right? So the second is, does that actually solve problems in every application domain? I'm not sure. So at first I was highly skeptical. Then as I kind of learned a little more about it, now I'm more convinced that event sourcing, like at least in certain applications, like makes a ton of sense. What I'm describing is a little bit different though. You know, event sourcing to me is how you maintain data within one application. I'm actually talking about how that data is communicated between all the applications. So if you think about some of the advantages that were in the earlier event sourcing talk, like, hey, I can take that log of changes and I can feed it to, you know, a search index and use it for ETL into my Hadoop cluster, and I can put it in a cache. Well, you can do that whether or not your database for your application is an event, you know, is event store or is Kafka, or is actually a regular database and you just capture changes from it, right? So Oracle has an API that will get you the log of changes from Oracle. Other databases have similar features. And so I think it's important to separate the event capture mechanism and what you do with that from the like implementation of the data store and how that affects the internals of your application. To me, the problem I'm most interested in is the kind of like how we all talk together problem. There, like if you go back to that immutability slide, I actually think the case for immutability gets stronger as you go up. So the for loop, it's like, you know, I don't really care if my for loop is, you know, I equals 0, I plus plus, doesn't confuse me. It's local to like this one little snippet of code. How data moves around an organization with like some hundreds of people or 1,000 people, I think that's like, you better have a really clear concept of immutability and flow and who gets what. And so like every, you know, level between that I think becomes more important to have a really crisp story around. Event sourcing is kind of in the middle. And so I think it has to play out when these things are always exciting. Then you see 100 applications built that way and you're like, okay, like it works for 30% of them really well. Hey, that's like an amazing accomplishment if you just changed 30% of, you know, applications. But I don't know if at least I have a good answer for what 30% that is. But I'm like not an expert at that. And it's also not really what the talk is advocating, to be honest. I think it's super compelling, and I think the like stream processing aspect of that is super compelling. Like being able to compute things that are, you know, in an asynchronous manner and having that be a simple way of writing code, I think that makes a ton of sense, regardless of whether you're using kind of a normal off-the-shelf database or a database which is rebuilt in this way to be more event-centric. One thing I would say for sure is like, overall, you know, computer science infrastructure has largely ignored the event side of things and focused on the state side of things. I think that's like way too much. So we're way too far on the state side. We need to come towards events, whether that's like all the way to where everything is just represented as events and you just derive all state off of that, or whether you need something that handles both state and events together, you know, maybe we'll know soon. I don't know. So that's a very vague answer maybe to your second question. I guess I am super excited about it, and we will see how it works out as an application development mechanism.
Thank you. I was curious, how do you handle a leader on a partition going down? How do you recover from that, and how long does it typically take for that to happen?
Yeah, so the way we do this is there's a leader for each partition that takes all the writes. Those writes fan out to the followers. And the obvious question is, well, what happens if the leader fails? And the answer is you need to make a new leader. And so we do that. We have like a central process in the cluster that decides all leadership information, because there's lots of these partitions. And so whenever there's a failure, it's like, OK, you were hosting 100 different things. You were the leader for 30 of them, blah, 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 blah. Here's everybody's new job. That happens very quickly. So it'll be proportional to the number of partitions that are getting failed over. But you know, like a few milliseconds per partition is reasonable. So in the case where you like restart a server, it will do this, you know, one at a time and then bring down the server. In the case where a server dies hard, well, first you have to realize it's dead. That takes a chunk of time, but then the leadership election is usually pretty quick after that. All right, last question.
You say that Kafka is, if you were to relate, a relational database to a
Yeah. So if I had a story that was as good as these Mesos people, I would say, yeah, it's like the commit log for your data center. But then everybody's like, what the hell is a commit log? So I don't know if that's as good. Yeah, no, so the usage is actually very similar to, in a database, the way a database works internally is you get an update, you commit it to the log, and then you're like, OK, now I got to update all my little indexes and derived data structures. If you crash in the middle of that, the log is the thing that happened, and you can catch up off of that. That's exactly the same mechanism you're using kind of at a larger scale to keep all these different systems in sync, right? You basically commit to the log, and then that write fans out to everything that needs it. So yeah, that analogy is pretty good. Cool. All right, thanks, guys. I'm super happy to take more questions, but I think I'm out of time, so.